Heat. So we want to look at heat capacity today and specific heat capacity. So heat capacity is basically the amount of heat that is needed to change the temperature of an object by 1 Kelvin, where 1 change in 1 Kelvin is the same as a temperature change of 1 degree Celsius. So our heat energy required is going to be given by the letter Q. And energy is measured in joules. Our change in temperature obviously is kelvins for our SI unit, but 99% of the time our questions are going to be given to us in terms of degrees Celsius. So the delta means change and theta means temperature. So that symbol is the Greek letter for delta and the Greek letter theta. And then our capital C is our heat capacity. So of course, if we're looking at getting the unit for heat capacity itself, well then that would be Q, the energy, divided by the change in temperature. And the unit for energy we see there is joules, and the unit for our change in temperature is degrees Celsius or kelvins. And therefore we say the unit for our specific heat capacity would be the joule per Kelvin. Okay, so if we're looking at this problem up here where we have a beaker of water has a heat capacity of 2000 joules per Kelvin, well, that's telling us that the heat capacity, capital C, is 2000 joules per Kelvin. Then it says, well, how much heat energy must be added, in other words, Q, in order for its temperature to rise from 4 to 96 degrees Celsius. So therefore our change in temperature is the difference between 96 and 4, which is of course 92 degrees Celsius. So for the amount of energy required to bring this temperature from 4 to 96 will be 2000 times 92, which is 184,000 joules. So in other words, the amount of energy required to bring the temperature from 4 to 96 degrees Celsius for a beaker of water will be 184,000 joules. Okay, so specific heat capacity. And this is the heat energy needed to change the temperature of 1 kilogram of that substance by 1 Kelvin. So it's more specific to mass in this case. So again, our formula is Q equals mc delta theta, where again our Q is equal to our heat energy in joules. M is the mass, which will always be in kilograms. So if we're given a question with grams in it, we have to instantly change it to kilograms. Same way if our energy is given to us in kilojoules or megajoules, we need to change that back to joules. Delta theta, again, is our change in temperature. And again, this will always be in degrees Celsius. And then small c this time is our specific heat capacity. So therefore, if I get C on its own, I have Q divided by M delta theta, which is joules divided by kilograms divided by our Kelvin. In other words, the unit for specific heat capacity is joules per kilogram per Kelvin. And again, so our formulas for heat capacity and specific heat capacity are in our maths tables. And in our maths tables, page 58, rather than Q, they tend to use delta E for energy change. So that's just something important to note, whereas our textbook tends to use Q for our heat energy. But both formulas are there side by side, classed as energy needed to change temperature directly under Celsius. whereas our units are page 65 and 66 in our maths tables. Okay, so even if you forget your units, they are still in your maths tables. So let's have a look at an example then that involves us finding our specific heat capacity. So on page 162 in our textbooks, we're going to do question 6 first of all. And we can see here we're given 11,088 joules of heat energy is needed to raise the temperature of 1.6 kilograms of copper from 7 to 25 degrees. So our change in temperature is going to be the difference between 25 degrees Celsius and 7 degrees Celsius, which is equal to 18. And it says that we want to find our specific heat capacity. So we're looking for C. So we have Q equals mc delta theta. And you can choose to rearrange the formula first or at the end. That's up to yourself. So if we sub in our values, we have 1.6 times C times our change in temperature, which is 18. And therefore C is equal to 11,088 divided by 1.6 times 18. And that gives us a specific heat capacity then of 385. And again, our unit for specific heat capacity is joules per kilogram per Kelvin. Okay, so in question 12 then, same page, we're given the fact that we have 30 grams of water at 100 degrees Celsius, so boiling water, is added to 100 grams of water at 20 degrees Celsius. So if we add hot water to cold water, well, the hot water that we're adding is going to give heat to the cold water and it's going to lose heat. So the hot water will lose heat, the cold water will gain heat. And if there's no heat loss to the surroundings, what's our resulting temperature of the mixture? So basically what we have here, and it's kind of the key to most of our questions in heat, is that the heat loss is equal to the heat gain, provided we don't have any loss to the surroundings, which we're told here in the question. So what's losing the heat here? Well, the boiling water is losing the heat, the water at 100 degrees Celsius. And what's gaining heat? Well, the water that it's put into is gaining the heat, and that's the water at 20 degrees Celsius. So a lot of the times we can have, hot metal, like a lump of hot copper is added, or we have hot copper is added to water in a copper calorimeter. So these questions kind of build as we go through the chapter. So today we're just looking at heat loss and heat gain, so keeping it relatively simple. So what's losing the heat? So if it's losing heat and we have the mass, then we're going to have our mc delta theta for the energy lost is equal to the mc delta theta for the energy gained. So the mass of the water that was at boiling point is 30 grams, but of course that's going to have to be changed to kilograms. So if we divide 30 by 1,000, we end up with 0.03 by our specific heat capacity. Now, if we go to the top of the page there on page 162, we're given the specific heat capacity of water to be 4,180. And we're also looking for the temperature change. Well, it starts at 100 and we don't know what it ends up at. So in other words, we don't know what the final temperature is. Now that must be equal to the heat gained. So the heat gained is the water that it was put into, which was 100 grams of water. And again, if we have 100 grams, we need to change that to kilograms, which is 0.1 times the specific heat capacity of water. Well, that's still 4,180 times the change in temperature. So this time it's going to increase in temperature. So we don't know what the final temperature is, but it's going to be higher than 20 degrees. So of course it has to be the final temperature minus 20. So you have to make sure that we have that the right way around. So again, that's the final temperature there. Okay, so let's multiply out our brackets here, and then we're going to have to get our theta on its own. So if I multiply out the left-hand side, I get 12,540 minus 125.4 theta. And on the right-hand side, I get 0.1 times 4,180 is equal to 418 theta minus 0.1 times 4,180 times 20 is minus 8,360. So if I bring all the thetas to one side, so I'll have 418 plus 125.4 gives me 543.4 theta. So the final temperature is equal to 12,540 plus 8,360. So it's 20,900. And therefore the final temperature, if I divide across then by 543.4, I end up with the final temperature to be 38.46 degrees Celsius. So in other words, the boiling water has gone from 100 degrees all the way down to 38.46, and the water 20 degrees Celsius has increased in temperature to 38.46 degrees. In other words, when we mix the two together, that's the final temperature that we end up with. So what you're going to do for me now on page 162 is question 1, 2, 3, 5, 8, 10, 11 and 13. So that's 1, 2, 3, 5, 8, 10, 11 and 13.